So as we just saw, alcohol can make foods resistant to spoilage. But of course, in the world of microbes, there's always going to be some bug who has learned to utilize a food source that no one else can utilize. And it turns out there's also a bug who can utilize ethanol and turn that into food and energy to live. So this happens if you just let wine sit around. If you actually don't drink your wine, but you just let it sit on your shelf the way you would with whiskey, the wine will over time turn into vinegar. And so if you've ever opened a very old bottle of wine, you may have had this experience where you're very excited and then it just tastes really sour and disgusting and vinegary. So two microbes that can do that are Acetobacter and Gluconobacter bacteria. And so here's the reaction for the ethanol turning into vinegar. So here's the ethanol, and it reacts with oxygen. So this is under aerobic conditions, meaning there's oxygen around. And this turns into carbon dioxide and acetic acid, which is vinegar. Vinegar is actually a very powerful microbial agent. It turns out that as little as 0.1% of vinegar in a solution kills most microbes. And so if you have ever pickled, sort of done a fast pickling recipe for cucumbers or other vegetables, you may have done this by not going through the actual fermentation reaction, but you've just added brine, which is salt, which is also antimicrobial, and you will have added some vinegar, and this makes it keep longer. It's not true fermentation, but it kills enough microbes so they can keep it for a long time in the fridge. So given what we learned from our calculation of turning sugar into alcohol in wine, we can now use the same principle and try to figure out how much vinegar we get from turning ethanol into acetic acid. And so we can just use this equation that we have here, and knowing that we started out with 1.6 moles, and this is what we got earlier from our wine calculation. We started out with 1.6 moles of ethanol, and since the reaction is balanced, we get 1.6 moles of vinegar as well, and this is then in a solution which is a total of 750 milliliters. So we can divide this and we'll get a final concentration of 2.1 moles per liters. So this would be our final concentration of vinegar in the solution. And maybe from this we can now figure out what the pH of vinegar should be. So let's see if this works out. So the vinegar, of course, sitting in solution is going to it's not a strong acid, it's a weak acid, which we've learned about earlier. So it's going to dissociate into an acetate ion and into H+ ions. And we know, so we can look up what the equilibrium constant for this is, and it turns out it's 1.8 times 10 to the negative 5. So if we then set up the equation for the equilibrium constant, which is the hydrogen ions times acetate ions over our initial reactant, which is the acetic acid, this should equal the equilibrium constant. And we know what our concentration of acetic acid is, and so we can solve for our concentration of H+ ions from this, and this turns out to be 0.0061 moles per liters. And of course, having our equation for the pH, which is pH equals minus the logarithm of the H+ concentration, we then get a pH of 2.2, which is actually a very good estimate for what a lot of wine vinegars are. Now, if you don't do the fermentation all the way, so for example, in balsamic vinegar, there may still be some sweetness left, and in other vinegars, you may start out with different sugar concentrations. You will, of course, end up with a different pH. So in some fruit vinegars, the pH is more like 4.5, 5. But for the case of wine vinegar, if we assume that all of the sugar turns into ethanol, and all of the ethanol then turns into acetic acid, this would be the pH we get, and this is actually quite accurate. Here now is a recipe for making your own vinegar from fruit, and in this case it's a pineapple vinegar. So here we're starting out not with wine and not with a normal sugar content, but we're starting out with pineapple. And the recipe is very simple. You just take the pineapple, you add sugar, you then add some water, and then you cover it with a cheesecloth and you put it in a dark, cool place from 6 weeks to 6 months. And every 2 weeks you add some sugar. So now what we just learned about how this process happens, every time you add more sugar, the sugar is turned into ethanol, and the ethanol is then turned into acetic acid. And gradually over time, we're increasing the pH, which means that fewer and fewer other microbes can live there, and the microbes that are producing the acid can thrive and take over the solution. So the important message then in all fermentations is that you need to kind of target the environmental conditions so that they fit the particular microbe you're trying to get more of. And so in this case, we want a presence of oxygen. So that is why we're just having this cheesecloth over. There is easy access of oxygen into the solution, whereas in other cases, as Dave Chang is going to show us, sometimes you don't want any oxygen there. And that is because you want to tweak the environment so that it is just slightly enough favorable for some microbes, whereas the other microbes are sort of taken over by the other ones.